Hello all. So in the previous lecture, we have discussed the two important properties of the waveguide: guide wavelength and phase constant. Okay. Now let us continue with the discussion of this characteristic parameters. So the next characteristic parameters that we discuss is about group velocity and phase velocity. So this is very important terms related to the waveguide. Okay, which we often encounter. All right. So what is this concept? Okay, so when generally whenever an electromagnetic wave is propagating, right, inside any media, that can be free space or any other, so it can have two velocities, right? So because an electromagnetic wave, right, especially in case of waveguides, so this right, there is a possibility of different modes propagating inside the waveguide, isn't it? So all these modes will have a different beta value. Okay, so whenever the beta is non-linear function of frequency, whenever the beta value is a non-linear function of frequency, as the case that we got in the last case, so beta is root of omega minus omega c square. So it is a non-linear relation. There is a non-linear relationship between the beta value and the gamma value, isn't it? So in such cases, whenever an electromagnetic wave is propagating through the media, and if the phase constant of this electromagnetic wave is not a linear function of frequency, there are two kinds of velocities that can exist for this wave. Okay, so one velocity is the velocity at which the phase of the wave changes. Okay, one velocity is the velocity at which the phase of the wave changes. Phase of the wave changes along the z-axis or along the propagation, along the direction of the propagation. Okay, so one velocity is the rate at which, the velocity at which, okay, or the rate at which, or the speed at which, right, the phase of the wave is changing. The phase of the wave is changing. Okay, or you can define it in another way. It is the rate, or it is the velocity at which the wave front, okay, of the equiphase, okay, of all the equiphase signals, the resultant wavefront is changing, right, in time. Okay, or along z-axis. Okay, so right, okay, one velocity is the velocity at which the phase of the wave is changing. The phase of the wave is changing. Okay, that means, right, for example, if I have a wave like this, so this is the phase. Phase is nothing but the starting point of the signal, right? The phase is nothing but the where the wave starts, or the wave is initiated with respect to some reference. Okay, so how does this phase of the wave changes? What is the rate at which it will changes? So that is given by a velocity, which is, right, one velocity, which is called as the phase velocity. Okay, the second is, right, another velocity that exists for this kind of waves is the group velocity. Right, it is the velocity at which, right, in case of multiple, right, for example, if I have multiple waves, okay, multiple waves of frequencies that are let's say closely separated to each other, of smaller frequencies around them, so it is the rate at which this combination, this group is propagating in the direction of propagation. Okay, so it is the right velocity or the rate at which a group of waves, a group of near frequency waves are propagating in the direction of propagation. Okay, so at the rate at which they are changing. Okay, so generally, if I consider, right, for example, if I consider a modulated concept, to just to illustrate, for example, if we consider I have a signal like this, a modulating signal, a carrier signal, all right, and I have got a modulated signal, which is, right, generally a envelope, isn't it? So if I consider an amplitude modulated wave, so the resultant of all these things, right, the resultant of modulation will be an envelope. Okay, so and inside this envelope my frequency will be, my variation will be like this, isn't it? So right, the group and phase velocities, how I can express them is, so right? Group velocity is the velocity at which this envelope is propagating. Okay, right? So it is the velocity, right? If I consider this as the direction of propagation, so the velocity, for example, I have a point here. Okay, so it is the rate at which this point is propagating along the z-axis. It is moving, right? So that envelope is the resultant envelope itself is moving. Okay, so it is the resultant, it is the velocity at which this envelope, okay, or at this combination of all the groups, right, the final wave that we get, the final signal that we got, so the rate at which that particular wave is moving, right, inside the waveguide is called as the group velocity. Okay, so let us be very clear. So a group velocity is also called as envelope velocity. Why? Because this is the concept, right? So, right, it is the velocity at which the combination of, right, the combination of all the terms, all the waves of similar frequencies, or right, dispersive frequencies, right, okay, form an envelope, and the rate at which this envelope moves inside the waveguide. Okay, so the rate at which that envelope is moving inside the waveguide is called as the group velocity. Whereas phase velocity means, right, inside this waveguide, the carrier or the several frequencies will be there, na? Right? So what is the rate at which this particular, right, what are the particular components that are moving inside the waveguide? So for example, I can have a resultant wave like this, okay, and I can have also, let's say the resultant wave is same, okay, but here let's say the rate at which the wave is moving is like this. Okay, then I can have a wave like this. Okay, same wave, right? Okay, I can have inside the waveguide the my right, the structure is like this. So I got three cases, 1, 2, 3, right? So okay, in each case let us assume that the envelope is moving with the same velocity. That means the velocity of propagation of the combined wave is same. Okay, so the rate at which these, right, waves move inside the waveguide is called as group velocity. But in the wave front, in the envelope, we can see that the resultant components, whatever the individual components are there, right, you can say that as carrier, or carrier. Generally, if I consider the modulation case, this will be the carrier signal, right? So the carrier signal is changing in each case. That's why we got this wavefront. Okay, the wavefront is nothing but the sum of addition of all these points, isn't it? Okay, so the rate at which, right, this carrier is changing or the individual components are changing inside the wavefront is called as the phase velocity. Okay, so here you can see this wave and this wave, they might have the same velocity of propagation, right? That is, the group velocity is same, but here the phase velocity is different, here the phase velocity is different, and here the phase velocity is different. Okay, so the rate at which the individual component is moving inside the waveguide is different for this case, for this case, and for this case. Okay, so this is what we call it as phase velocity, right? Here the phase of the signal is changing very slowly. Okay, here the signal phase is changing very rapidly. Here it is, right, medium. Okay, so phase velocity is low here, very high here, moderate here. Okay, so this kind of thing is what we call it as phase velocity and group velocity. Okay, so in short, group, right, phase velocity means it is the velocity at which the phase of the electromagnetic wave is changing. Okay, generally this represents the rate at which the individual components inside the waveguide, the field patterns inside the waveguide, right, change. Okay, how they change is what we call it as, right, phase velocity. Whereas group velocity means it is the velocity at which the resultant group, the group of waves, or the right, the set of waves are traveling. The resultant wave is traveling inside the waveguide. Okay, so this generally, right, is obtained by the combination of all the waves and how this resultant wave is propagated. Okay, so it is also called as envelope velocity. Okay, in case of free space or in case of two-way transmission lines, we don't get the phase velocity and group velocity to be a lot different. Okay, especially in case of free space, right? Because in case of free space, the phase constant beta, it is it is a linear function of frequency. So therefore, in those cases, right, we don't have phase velocity and group velocity to be different. Both of them are same. Okay, they exist, but both of them are same. Okay, because beta is a linear function. We will see, right? The phase and group velocities, they depend on beta value. So, right, therefore, okay, if beta is a linear function of frequency, then both these two values will be same. There is no difference at all, right? And we will not get any problem. But whenever, right, beta is a function of a non-linear frequency component, or if it is a non-linear function of the frequency components, then we will get phase and group velocities to be different. Okay, so that is the case which happens in case of waveguides. Okay, any waveguide, rectangular, planar or circular, all these waveguides are having a non-linear relationship or non-linear function of beta in for frequency. Okay, so therefore for each case we will get phase and group velocities to be different. Okay, so phase velocity, right, is the velocity at which the phase of the wave changes along the z-axis. Okay, right, whereas group velocity is the velocity at which the resultant group is traveling at the with respect to the right direction of propagation or along z. Okay, now let us derive these expressions for phase and group velocities. Okay, right. So in case of a planar waveguide, let us derive the expressions. Yeah. So this whatever the derivation we are going to discuss, this will be same to both planar waveguides and rectangular waveguides also. Rectangular, circular, anything, because it is not dependent on the type of waveguide. It is a common one. Okay. Yeah. Let us derive that. So generally, firstly, the expression for phase velocity, we write it as Vp is equal to omega by beta. So omega is the angular frequency and beta is the phase constant of the waveguide. Okay, right. So firstly, for the expression for phase velocity, let us derive the expression for phase velocity. So in general, phase velocity is given by Vp is equal to omega by beta, where omega is the angular frequency and beta is the phase constant. Okay, right. Now, now from this, right, just now we derived an expression for we derived an expression for beta. So let us substitute that here. Omega by beta is equal to root of mu epsilon into root of omega square minus omega c square. Okay, isn't it? So this is what we got the expression for beta. Okay, yeah. So let us substituting that. So 1 by root mu epsilon, I'll keep it aside. So I'll take this omega down. So 1 by root of, okay, so I take that omega down and I take it into the square root. So omega square minus omega c square by omega square. Okay, so that's what I get. So this is equal to, right, 1 by root mu epsilon into root of. So if I get if I cancel out omega and omega square, so I'll get 1 minus omega c by omega whole square. Okay, so right, generally phase velocity Vp is equal to 1 by root mu epsilon into root of, sorry, so 1 by, okay, yeah. So this is equal to 1 by root of, okay, 1 minus omega c by omega whole square. Okay, correct. So okay, so this is one expression for phase velocity, right? Phase velocity is given by Vp is equal to root of, right, 1 by root over 1 mu epsilon into, right, 1 by this thing. So but generally we know that root of 1 by mu epsilon, 1 by mu epsilon, right, 1 by root mu epsilon, this is nothing but, okay, the velocity in the free space. Okay, velocity in the free space. So we can take this as c. Okay, so it is generally the velocity of the free space or the velocity of light inside the free space. So we can take that as c. So we can express, in that case we can express Vp as Vp is equal to c by root of 1 minus omega c by omega whole square. Okay, so this is the expression for phase velocity. Okay, so phase velocity, right? So in general, phase velocity is given by Vp is equal to omega by beta. So omega is kept as it is. Beta, just now we derived in the previous lecture, we have derived the expression for beta. Beta is equal to, right, root of mu epsilon into root of omega square minus omega c square. So from this, right, 1 by root mu epsilon, okay, 1 by root mu epsilon into what is this term, omega square minus omega c square by, I take this omega down, so omega square. So omega square gets cancelled, 1 minus omega c by omega whole square. Okay, so from this Vp is equal to root of 1 by mu epsilon into, okay, so 1 minus omega c by omega whole square. Now, right, since root 1 by root mu epsilon, this is nothing but the velocity of free space v. Okay, so I consider this as c or v, whatever we can take. So Vp is equal to c by root of 1 minus omega c by omega whole square. This is the expression for phase velocity of the, right, wave. Okay, so this right is a simple derivation. Okay, right. Now let us similarly derive the expression for group velocity. Okay, so group velocity is given by, so the general formula for this group velocity, it is represented by Vg. So Vg is equal to, group velocity is equal to d omega by d beta. Okay, so it represents the rate of change of angular frequency with respect to, right, the phase constant. Phase velocity represents change, right, a ratio of angular velocity to, right, beta. So that's what we said. If beta is a, right, linear function of omega, then group velocity will become approximately same as that of phase velocity. Okay, right. If not, then group velocity will be different. Okay, yeah. Let us derive the expression for group velocity. So because we don't know this, let us take beta first. So beta is equal to root of mu epsilon into root of omega square minus omega c square. Okay, right. Now I'll differentiate this beta with respect to omega. So d beta by d omega is equal to, this is a constant, so we can put as it is root mu epsilon into, so root x. Root x means 1 by 2 root x. So omega square minus omega c square into, again, differentiation of this. So omega c is a constant. Okay, here we are differentiating only with respect to omega. Omega c is a constant. Okay, so we can take that out, right? So that will become 0. So differentiation of omega is 2 omega. Omega square is 2 omega. Okay, so 2 gets cancelled here. So this is equal to, right, what I get, okay, root of mu epsilon into omega by root of omega square minus omega c square. Okay, so this is what I get, isn't it? Okay, now let us take the reverse, because group velocity for us is reverse of this. So therefore, taking the reverse of this, so yeah, let me write it here. D omega by d beta is equal to, so d omega by d beta is equal to, so this will become 1 by root mu epsilon into, right, reverse of this. What is the reverse of this? Root of omega square minus omega c square by omega. So this is equal to 1 by root mu epsilon into this. If I take omega into common, so this will become 1 minus omega c by omega whole square. Okay, yeah. So right, again here also, right, if I take 1 by root mu epsilon as the free space velocity c, right, so then I will get the final expression for my Vg as Vg is equal to d omega by d beta is equal to, right, c into root of 1 minus omega c by omega whole square. Okay, so this is the expression. Okay, right. So okay, so again, just simple derivation. So group velocity is generally given by rate of change of omega with respect to beta, so d omega by d beta, but I don't know this expression, I don't know the value of omega also. So what I know, I know is beta, so I'll take beta as equal to root of mu epsilon into root of omega square minus omega c square. So from this, okay, so differentiating this with respect to omega, so d beta by d omega is equal to, right, root of mu epsilon into, right, the derivation of this root x 1 by 2 root x, okay, into, right, again the differentiation of this omega square, that is nothing but 2 omega. So 2 gets cancelled, so I will get omega by root of omega square minus omega c square. Now, right, I want the group velocity, which is nothing but Vg is equal to d omega by d beta. So I have d beta by d omega. So let us take the inverse of this. So when I take inverse, I'll get like this. Okay. So from this, all the things. Okay. Here 1 by root mu epsilon. Again, it is nothing but the free space velocity. So I consider it as free space velocity. So I substituted c here. So I'll get like this. Okay, right? So this is the expression for group velocity. Okay, so in both whenever we are calculating both the phase velocity or group velocity, the point that we have to understand is we have used the relation of beta directly. So but in exams, whenever they are asked for right long questions, okay, so we have to derive this beta first. Okay, derive the beta first. Okay, and then from that use this beta value to derive the group and phase velocities. Okay, all right. Yeah. So okay. So for any electromagnetic wave, there will be two velocities, right? Okay. There will be two velocities for it. One is the velocity at which the phase of the wave changes, and other is the velocity at which the wave itself propagates, or the wave itself changes along the direction of propagation. Okay. So the first velocity is called as phase velocity, right, and the second velocity is called as the group velocity. Okay, so write Vp and Vg. Okay, now we got the expressions for Vp as Vp is equal to c by root of 1 minus omega c by omega whole square. Okay, and Vg, the group velocity Vg is equal to, right, c into root of 1 minus omega c by omega whole square, isn't it? So these are the two expressions that I got. Okay, right now. Okay, now okay, so in general, right, okay, this same expressions that we got in for Vp and Vc, we can also express them in terms of lambda. Okay, in terms of wavelength and frequency also. So here omega c is angular frequency, which is nothing but 2 pi fc, and similarly omega means, right, 2 pi f. Okay, so substituting that, so I'll get Vp is equal to c by root of 1 minus, okay, 2 pi fc by 2 pi f, 2 pi gets cancelled, so this I can simply write it as fc by f whole square. Okay, and similarly Vg is equal to c into root of 1 minus fc by f whole square. Okay, so right, in terms of frequencies I'll get like this. Okay, right, next we know that the wavelength, what is wavelength? Lambda is equal to, right, so lambda is generally equal to c by f, isn't it? So lambda is equal to c by f, and lambda c is equal to again c by fc. So if I take the ratio of lambda by lambda, okay, c, so c by f divided by c by fc, so cc gets cancelled, fc by f. Okay, so fc by f is equal to lambda by lambda c. Okay, so to differentiate, let us call this as lambda naught, where lambda naught is the wavelength of the free space. Wavelength of the free space. Okay, so lambda naught is the wavelength of the free space. Lambda c is the cutoff wavelength. Okay, so in that case, okay, I'll get lambda naught by lambda c. Lambda naught is equal to c by f. Lambda c is equal to c by fc. So lambda naught by lambda c is equal to, right, fc by f. Okay, so using this we can express Vp and Vg in terms of lambda also. So Vp is equal to c by root of 1 minus fc by f is nothing but lambda naught by lambda c whole square. Similarly, Vg is equal to C into root of 1 minus lambda naught by lambda c whole square. So this is the expression for phase and group velocities in terms of wavelengths. Okay, this is the expressions for phase and group velocities in terms of frequencies. Okay, and these are the expressions for phase and group velocities in terms of angular frequencies. Okay, so all these three, we can use whatever based on our requirement. Okay, right. Clear with this? Yeah. So, and finally, one point related to this. So, whenever I multiply phase and group velocities, okay, that is Vp into Vg. Okay, Vp into Vg is C into root of 1 minus Fc by F whole square into, again C into root of 1 minus Fc by F whole square. Okay, isn't it? So, this is the case, right? Vp is this, Vg is this. So when I multiply these two, so this gets cancelled. So Vp into Vg is equal to C square. This is a very important relation we have to remember. Okay, so product of phase and group velocities will be equal to square of the intrinsic velocity or free space velocity. Okay, so Vp into Vg will be equal to C square. Okay, yeah. So this is the concept related to phase and group velocities. Okay, in the next lecture we will continue with the next terms that are